Retransmission.
So our next talk is about RIST, a reliable internet stream transport, a promising new protocol. Please welcome Kiran.
Thank you for the introduction, Christoph. If you want to email me or send me horrible tweets, you can tweet me there. So we would like to introduce RIST. Well, first of all, what are the goals of what RIST is trying to achieve? And the goals of RIST are low latency video between generally professional devices, or from point-to-point video or point to multi-point video, not necessarily to end users. So during the production process, often. So not in a browser, but between different video devices that are not browser-based at a really low latency. And the goal is really to have packet recovery on a lossy network. It says internet, but this could also be a lossy WAN of some sort. May not necessarily be the internet, or it could be a wireless link, for example, between two different places. And the other kind of goal is backwards compatibility. So at the moment, pretty much all of this stuff is done with a transport stream in UDP. And the goal of what they're trying to achieve in RIST is to do that, to have some level of backwards compatibility. So you could send to a non-RIST capable device, and it will at least operate normally. It may not be able to gain the benefits of RIST, but it will still work. So the background to this, who came up with RIST? This is unusually at an open source event. This is a specification written by a closed industry forum of manufacturers. But there's a bright side I'll talk about in a minute. And they have an interest in, there's a lot of this reliable internet streaming kind of technology already done in a proprietary domain at the moment. So there's lots of different proprietary protocols that people use, and they want the ability to have something open standard based, and ideally building on IETF. You can see that they've gone and done their own thing a little bit here, for rightly or wrongly, but the idea is to build on existing IETF standards, which are free and open source and published. And so RIST was published in October 2018. And what was unusual, actually, is RIST was published under a Creative Commons license. So usually most things in broadcast are designed actually to keep people out, to actually gatekeep, a bit like for scientific publishing industry. It's exactly the same phenomenon. Things are kept behind paywalls, they're kept behind secrecy, designed to make sure only a few people can implement it and a few people can understand it. And if you were here in the last presentation, and it's not Willem's fault because Willem is trying to improve things, but he used a lot of acronyms and a lot of terms, and this is all deliberately or otherwise there to make it not possible for people to understand, so that only a few people can understand this and make a lot of money out of it and not have open source implementation. So this is actually, although lots of the process was bad from an open source standpoint, publishing under a Creative Commons license is a big deal, because it lets people actually understand and implement this and find their problems, instead of, living in acronym soup where things are closed and yeah. So why not TCP is the question that's obvious, and I can't go into this because you could write a book about this. This is a whole research field in itself, but at least to begin with, traditional TCP drops transmission rate with packet loss. There's lots of work in other dev rooms you can find out about how they're changing that. And actually in our use case, we don't generally have throughput drops per se, and I'll talk about how that might be different later, but generally we just have random packet loss because of switch capacities, packet loss for other reasons, and we don't necessarily want, this is usually a constant bitrate transport stream, and we want still constant throughput, and we just want random packet loss to be fixed. UDP itself has native support for multicast, so I mentioned, for example, if you had a WAN, it's very common to multicast traffic across that WAN in a closed environment. It's quite easy then to have specific receivers request retransmits as a result. So a particular receiver can go and you could have a single sender sending to hundreds of different devices, and each receiver could go and request a retransmit in a multicast environment quite easily if there happened to be loss on a particular network segment. Backwards compatibility, as I mentioned again, want to send RIST streams to existing devices. It's also a lot easier in UDP land to do multipathing, to send traffic down multiple internet connections. And also the other interesting thing about UDP itself is, and this is becoming more common, for example, on the web with protocols like QUIC or HTTP3 now, lets the application handle all the congestion control decisions. And that means people can do all sorts of interesting things. You're not curtailed by the legacy of the kernel that the sender or receiver is using, which you may not be able to change in some cases. So what are things done currently? So what that people use currently, actually really basic 1990s technology, forward error correction. And this is an example of it, SMPTE 2022-1, really basic in this case. So it's built around the idea of these packet groups in rows and columns. So I don't know if you can see the colors very well, but row FEC is shown in blue. And as a packet is lost across a row, that's corrected using the FEC packet. And same with the columns. So if a packet's lost in a column, the red packet can be used as a very simple XOR operation, XOR operation can be used to correct that packet. But the biggest problem is those matrices have bounded size, and you can't handle any loss larger than the matrix. So retransmits are the other solution to this. So there's already existing open source software that does this. It's a problem certain people have been trying to solve since 2007. Aggregate RTP from Videolan was one of them. To be honest, the author did it when it wasn't cool. No one was really doing this at the time. This was considered not au fait, and now it's quite commonplace. Aggregate RTP is an example of such that. It lets you aggregate links, but also, as a side effect, has retransmission built in. There's also, as of last year, SRT from, I think it's a Canadian company, High Vision. It's a pretty monolithic code base, I would say. It does the same thing. It does retransmits. Quite bizarrely, I would say personally, they've built it around a file transfer application and then added live. The big downside is it supports single link at the moment. My understanding, but someone can shoot me if I'm wrong, is they have a proprietary add-on that does multiple links, but shoot me if I'm wrong. One big advantage, it has built-in encryption. That is a big thing. And to be fair to them, it's a very complex code base, and people have asked for a specification, and they actually wrote one to my shock, and it's actually 89 pages and exceptionally detailed. It's a very complex protocol, and to be fair to them, if someone actually had to, multiple people sat down and actually wrote this thing, which was amazing. And as I mentioned before, various other proprietary solutions, and they're all some variant of the FEC I showed before. Usually, hopefully something more advanced than this 1990 stuff, so there's much more advanced FEC out there that has much better protection and retransmissions. So they're mixing some kind of solution around that. I forgot to mention before, the other downside of FEC is there's quite a lot of overhead. So if you don't actually have loss, you can waste up to, I think, 25% overhead just adding these matrices that you won't actually end up using. So sort of a quick primer to RTP, a real-time transport protocol, and RTCP, it's a real-time control protocol. I think that's right. These are the main protocols used for UDP-based live video. For example, WebRTC is another example, uses RTP, various other applications. So usually the main traffic is sent on port N, and then N+1 is for the control and feedback data. So what the sender does is periodically send RTCP packets on port N+1 to keep state. And I'll have an example of that in a minute. So the receiver responds using receiver report RTCP packets. And it's grandly described as NAT traversal, but it's not really NAT traversal per se. As I'll show in a second, this is a particular standard functionality of NAT. And what's useful is this RTP and RTCP can be over multiple links. So main content, usually video, goes over the main, port N, and RTCP over N+1. So this diagram shows NAT traversal, quote unquote, in action. The sender sends that's not too bad. Sender sends RTP feeds. Usually the sender is behind a firewall, so I can rock up somewhere like FOSDEM, as hopefully this will be able to show, plug in. That's usually NATed. And receivers are usually in a sort of central facility where port forwarding and firewall, access control rules can be done. So sender sends a feed down port N. RTCP packets go across on N+1 to the receiver behind the firewall. The receiver then swaps the source port and destination ports, sends return messages back to the external NATed source port, and as a result, the stateful NAT passes it through. So this actually surprises lots of people when they realize you can do that, but this is exactly how DNS works. So you do DNS. When you do DNS, it sends a UDP packet out to a DNS server. You're NAT at home, assuming you're using 1.1.1 or 8.8.8, not your router's DNS. You send out UDP packet to one of these DNS servers, and it responds in exactly the same fashion. So that's why I was saying it's a bit grand to call this NAT traversal. This is basic NAT functionality. But some people seem to think this is a bit, this seems to be traversal based. So, acknowledgements. So, again, RTP 101, sorry if you're already aware of this, every RTP packet has a sequence number, so it has a number that increments for every packet. Unfortunately, it's 16-bit. Probably the RTP developers back in the 90s couldn't really foresee actually bandwidth is quite high. So 16 bits actually wraps around pretty quickly these days, certainly on high bitrate video, very, very quickly in uncompressed video. So here's an example of what a negative acknowledgement looks like. So this is not like TCP where there are ACKs in general. This is just negative acknowledgements. So packets which aren't received are requested for retransmission, and I'll show you a bit more about that in a minute. So first packet comes through, second one fails. The receiver then requests a retransmit, and the sender then transmits it back. And I'll explain how the signaling works in a second. So there's two types of negative acknowledgement message. The first of which is a bitmask. This is already IETF standardized, already exists for I think decades probably. And it uses a base sequence number. So the bits in bold are just the codes to identify that type of RTCP packet. It uses a base sequence number and a bit mask. So in this example, the base of 100 is lost, and then there's a 16-bit mask showing how the next following 16-bit packets, whether they've been received or they've been lost. And then you just add more and more of the bottom fields along to show subsequent packets being lost. And this is really useful for just random packet loss, the odd couple here and there. And then they've gone now and decided to do their own thing a bit, and implemented ranges. So this is where you have a range. So if say I lose 100 packets, this field, this type of packet is designed to signal ranges at very low, very, very quickly. So they've used a application-specific type 204, and there's a ASCII string RIST to signal that, and you can see that they're losing packets at the bottom. So I think they start at 102, they lose 19 packets. To be honest, this is kind of pointless. This is over-engineering. If you've lost that many packets to begin with, the overhead of adding a few more of these isn't going to sort of be consequential, because you're going to have to retransmit so much. You're going to save a few bytes for sending a range packet, but so what? You're going to have to send huge amounts of it back anyway. It's not as if the return channel is going to be busy. And so how does the receiver know when it's received a retransmission as opposed to a main? They've done this in a really bizarre way. So the SSRC, I think, is the source. It's basically, I forget the acronym now, but it's essentially an identifier for the source. And what they've done to signal a retransmission is set the lowest significant bit of the SSRC to 1, which is a really bizarre way of doing it, because there's already an existing standard, RFC 4588, which you can look up, and you can see there's already a way of signaling exactly how it should have been done. So they've come up with this hack to do it. But as long as the decoder then knows what the retransmission is, so it looks at the LSB and says, oh, it's 1, so it's a retransmission, then it can figure out it's a retransmission and put the packet straight into its buffer where it needs to be. And then the rest of it, as I mentioned, becomes application specific. So the rate at which the receiver requests retransmits, that's completely implementation defined. So it means people can do all sorts of weird trickery if they wanted to. There's a whole bunch of problems that are just completely independently defined. How to handle. So let's say the connectivity cuts for a second or 2 seconds, and you have to retransmit, tens of thousands of packets. How do you handle this thundering herd response? And that's an implementation defined problem. That's not really. We're not even sure how you could really explain it in the protocol itself. So implementation-wise, there's 2 open source ones that I know of. There might be some others. There's UPipe, which will, in the examples directory, hopefully I will take the risk of the live demo and show you that. And there's VLC in, I think, 4.0, if JB's here, which has the RIST protocol. And there's a bunch of proprietary solutions, VideoFlow, Zixi, and I think also some hardware ones. So we've tested all 4 of those in combination, and they can talk and request retransmits, and they work fine. The hardware ones, if someone wants to give me some hardware to test, yeah, sure. Future work. Encryption, so you could already do encryption at a different layer, so you could run a VPN between your devices, for example. That works perfectly fine. But you may also want to do encryption in the protocol itself, and this will probably be DTLS. Null packet removal in the protocol. So lots of streams have null packets. If the content's not difficult, it's still padded to CBR, and you'll see in a minute, most of the streams that I'll show on the demo will be null packets because they're just one solid color. Bitrate changes, so there can be a point where the actual link throughput capacity drops and you'll want to actually change the encoder's bit rates. So how do you signal that? There's already IETF work to do this because in video conferencing this is already a thing. Pull mode, I'm not sure if they want to do that as part of the protocol, but I mentioned the decoder needs port forwarding. You could have a situation where your encoder is actually not in front of the file, your decoder is behind NAT, and how do you get the protocol to work without port forwarding? And there's various things. For example, VLC can do this already with RTP via, I think, RTSP, but that needs to kind of be implemented a bit differently. They also then the bottom bit is for when they're going a bit crazy. Scalable video, for those who aren't aware, scalable video is when you have a video stream that allows you to lose data but still recover sort of a lower resolution copy or a lower frame rate copy. This is really nice in theory. It doesn't work in practice. It's often easier just to, as you see now on the web, for example, just encode the video at multiple bit rates and switch. People have tried scalable video. I'm surprised they're reviving this 2000 era technology because very few people can do it right. It's very, very complex to implement and the benefits kind of aren't there often. Then this is where they go really, really crazy. Retransmissions on uncompressed video. So Willem told you all about the complexities of doing uncompressed video and all these crazy rules. And now they want to add retransmissions to that. So already in the tens of gigabits of range, and now they want to add retransmissions for some reason. This is where I think they're slightly losing the plot a bit. But yeah. Right, this is always the tricky bit. Live demo. Over the FOSDEM Wi-Fi, could we actually get a stream? Oh. This is well. I think the hardest bit of the live demo is will the HDMI work, or will we be using XRANDR? So I did cheat a bit, and in hindsight, maybe the cheating was oh yeah.
Okay, so you have to control to mirror.
Kinda. Not sure why it's showing a quarter of the screen, but so be it. Oh no, I think it's just resized and VLC hasn't gone and resized itself. But anyway, so I was hoping to cheat, well, and we did cheat by using a VPN. But what we discovered kind of during testing is most VPNs, so we were using WireGuard in this case, but a lot of VPNs can't handle pumping 50 megabits of UDP traffic through them. They just collapse. So no, but. No, but we want to show. I want to show the command line as well. All right. I just forget about the corner. So I actually want that. Right. So can you expand that a bit so I can actually. So you can actually see it is correcting packets as we speak, which is good. This is one of those fancy touchpads that does it. There we go. That's exactly what I want to see. So the sender, so this is a UPipe-based encoder in the office, and the UPipe example decode receiver here, and then that's being pumped into VLC for testing. So what you can see is the sender and receiver are estimating round trip times. They're calculating round trip times throughout the process. So I think it's every second, and as a result, the receiver is using that to figure out how many retransmissions it can send within the bounds of latency that's configured. So I think it's configured to 1 second latency, if I recall correctly, or maybe 3. Yeah. So unfortunately, when I want to talk about repairs, it's actually stopped repairing, but it was repairing a lot before. So and you'll see a ton of green terminal input, but you'll see it send retransmissions, and you'll see that it's actually lost nothing, which is quite good. I think the stream is 10 megabits, or did you cheat and lower it?
No, it's 10.
It's still 10 megabits, but the intention was to do 50 and really saturate the Wi-Fi, but that probably would have killed all your other devices. But never mind. It's not doing any repairs, but you should be able to see it send repairs packets if it was repairing. But Sod's law, when I want to talk about repairs, it doesn't. And when we're
Say repairing is never necessary, also.
well, I don't know, like it was. There we go. There, it's doing some repairs. So you can see that it's found holes between 9968 and 1994, and it's requesting retransmissions and gradually repairing them. It's found another hole and it's sent another retransmission. But and you can also see, since I Oh, I have 21 seconds left. So, since I think we configured it to 1 second, that gives me about, I have about a 20 millisecond ping to the office. So that gives me 50 different attempts roughly to retransmit. So there's a very good chance I'll be able to get that packet back. So live demo kind of worked, which is, yeah, that's great. Anyway, thanks a lot.
Any question? Yep.
In your future work items slide, there was no mention of any sort of multicast or multi-routing. Is that stuff that they're considering and it's just way far off, or do they consider that added to the domain?
What do you mean by multi-route? So, because I
Like-
talked about multiple links, that's already supported. So that's already part of the protocol. It recommends you send the retransmit down both links, and you duplicate the retransmit down both links. And it's again implementation defined how you want to balance the links. That's completely up to the way the sender and receiver want to do it. That's
And multicasting?
already supported again at the beginning. So the receivers, a multicast receiver requests retransmissions from its source, and it's recommended. Actually, I think you have to do it that way. You have to include your retransmissions in the multicast so that all receivers can benefit from the retransmission. Because the chances are, if let's say there's a trunk line, there's loss on a particular fiber line in that part of the world, the chances are there's quite a few receivers that have actually lost the packet. So all receivers can benefit from it.
Thank you.
Somebody there? No, but for the online audience.
You need it for the stream.
Yeah, I forgot to repeat the question. Sorry. So the question before was about multicast and multi-links.
Question, is this protocol also designed with 5G in mind, like where you can have network slicing and set up different quality of service levels?
I'm not the expert on 5G. There are people in the room who are. Where me? I'm looking to look at him, but I can't see him. Oh, he's there. No, but it supports UDP. So it's UDP, so you can set the type of service and diffserv flag, which is what people do.
Because it would have been nice if it would have been aligned with actually like the network link and what you're going to use.
You can set, yeah, and from what I understand from 5G is
because you have low latency on 5G.
yeah, but I think you could if the operator would sign the right commercial agreement with you to support TOS and diffserv, they could follow the rules theoretically. That should be possible, and it was marketed also possible for 4G, and it never happened. But so we'll see. I believe for 5G,
5G supports multicast. There are projects, 5G media project, where they're looking having multicast links over
so
5G.
does 4G, if I understand correctly, but for EMBMS, it's some kind of multicast, but that was not widely deployed. So it's more of a theory versus practice problem. But yes, you could do it, I think, with TOS and diffserv, surely. But
have you done benchmarks against existing retransmit-based type things like SRT, like you mentioned, or Quick?
Yes, we have, but I think we saw, from what I understand from, this is what Raphael told me. I forgot the last slide actually, which is thanks to Raphael and because it's on the wrong producer, but thanks to my colleagues for doing this work. So we have done some testing, and from what I understand, we are as good as, if not better. But this was I only got the data literally yesterday. No, literally this morning. So I haven't verified it myself. So.
Other questions? No?
Thanks.
Well, thank you, Kiran.